This is part 2 in a series of videos in which I am repairing this. It is part of a PDP-11-3. Now, someone did point out in the previous video, the comments in the previous video, that this is not actually a PDP-11-3. But what he's actually talking about is the assembly for the CPU. And it kind of depends on how you look at it, so I don't want to get into a long drawn out discussion on the history of these, but I will refer to this as a PDP-11-3. That's what the designation for the machine this comes out of is. This is referred to slightly differently, but there are different variants of the CPU assembly for these. But this one is the machine with the LSI 1102 processor, which is the processor I showed you in the first video, and I also said that it had the optional LSI device in there for the extra instructions. I stand by that. It's a floating point unit, but it gives access to the floating point instructions, and that's specifically why it's there. Without that floating point unit, you won't be able to run the floating point instructions. I was just trying to keep the explanation on target, on track. This is a repair video. It's not a detailed history of these machines. So the discussions can get kind of complicated, which is why I tend to simplify them, and I tend to refer to the name of the base machine and model series number rather than the specific build, unless that is specifically important to what we're discussing, which it isn't at this point. It might be later on, but at this point it isn't. So hope that made sense, and that is true of all my videos. I try and keep the explanations as simple as possible and try and keep the video moving along. So that said, in the first video I introduced this, I showed it booting up, but the problem is that it's not going through the proper sequence once the main program starts. It's part of a CNC system, so when the main program is started, we should be seeing the values for the X, Y and Z encoders shown on the terminal, and we weren't seeing anything. We were seeing the startup code and nothing else. The system didn't seem to crash. It wasn't hitting the reset vector, so something strange is going on. Now, I very much doubt it's a problem with the encoders. I don't actually have the encoders here, but even with them not fitted, I would have expected some data to be available. Now, it's possible those encoders are generating an interrupt when they're fitted, but from what I can gather, the values show on the screen even when the unit is removed from the main CNC control. Even if the encoders aren't connected, I believe something was still showing on the screen, which it's not with this machine. I can't confirm if that's true or not, but the first step is to try and figure out what is going on with this. Now, in CNC machines, one of the important aspects of them is timing, and because it's a multi-axis, I think this machine can support up to, I believe it's 6 axes at once, and because of that, in a CNC environment, you have to effectively control all the axes that you're dealing with in a very timely fashion, otherwise you'll get stepping in the CNC machine itself, which you don't want. So in order to make these efficient, quite often the code is copied from ROM into a bank of RAM to make the overall system much more efficient. And I believe that the issue here is not with the encoder circuits or the encoders themselves. I believe it's with RAM. So what we're going to do here is do some very basic RAM testing. So I'll get the machine booted up, and then we'll move over to the terminal and just do some very simple RAM tests. I will write some bitwise RAM test programs later on, but for now I just want to test the blocks of RAM. So we've got a RAM card in here, and I want to see if all the RAM chips are fundamentally working. We can do that in a very quick and easy way using the terminal, and that's why I wanted to just prove that the RS-232 access via the terminal was working. Okay, so we'll get this booted up. Okay, and now we'll move over to the terminal and see if we can test the memory. Okay, so as we can see, we've got the boot up prompt on the terminal. So what I'm going to do now is just do some very simple RAM testing. And I happen to know the main RAM in this machine is mapped starting at address 0. So we'll start there. Now these numbers in an octal, so just bear that in mind. So we'll start at the first address, and I'm going to try and write a value of 0 to this address, and then we'll read that back and see if we get a value of 0 reading back. Which we do, so that is this top number. This system automatically increments to the next address. But we are reading a value of 0, as we can see here. So we'll now try writing a value of all 1s to the same address. And we'll try reading that back. And as we can see, we are successfully reading this back. So what I'm going to do now is go through, and at increments of 100 octal, we'll check every single address in that range. So the next one will be at 0000100, and we'll do exactly the same thing. You can see currently it's set to 040004. We'll change that to 0. See if that reads back correctly. Which it does. So again, we're getting 100 here. So I'm going to do this now, and I'm going to go up through the entire address range for this first block of RAM, and if I find anything, I'll come back and we'll go from there. Okay, well, something interesting has come up here, in that I've just got to address 2000, so I've gone through in 100 octal increments. I've just tried 2000 and done this once, but I've written a value of 0, but reading it back, it's coming back as 004000. So we'll try do that one more time. So this is at address 20,000 octal. So I'm going to try and write a value. It's currently got a value of 004000. So I'm going to try and write 0 to that again. And read it back, and it's still showing us having a bit set. So we'll try setting a different value. So this time I'm going to try and set 111000. Again, remember this is octal. And we'll read that back. And again, the same bit is showing as stuck. I'm getting a value here of 115000. We'll try another value. And we'll read that back. Sorry, I've written the wrong address there. Try that again. So again, the same bit is showing as stuck. We'll try one last value. I'll try and set all the bits to a 1. And we'll read that back. So that's reading correctly, but then the bit's stuck at 1, so it would do. It's only if we try and set that bit to a 0, so we'll try that one last time. And read it back. So we definitely have a problem with the RAM in this machine. It could well be what's causing the problem. So what I'll do now is in the next video we'll take the RAM card out and start investigating the individual RAM chips, put a scope on it, see which of the devices appears to be at fault, and we'll go from there. But it definitely looks like we have a problem with the RAM in this machine. Okay, so that's it for this video. It looks like we have found at least one fault in this, and it is a sort of fault that would give us the symptoms that we're looking for. And the next thing I will do is start investigating the actual RAM card and see if we can figure out which RAMs are at fault and get them replaced. It is possible it's some of the glue logic that's causing this, but it seems unlikely because if it was that, we tend to get issues in all addresses. It's only at specific address blocks that we seem to have an issue. I haven't been through them all yet, but we have at least one fault, so we need to resolve that before we go any further.